Good day everyone, and welcome to our webinar on the subject of the benefits of 2D flood modelling. Apologies for the delayed start, folks. We just had an issue with the audio. My name is Peter Coombs, and I'm here with my main presenter today. That's my colleague Ludmila Fadeva. Ludmila is responsible for our XPSWMM, XPSTORM flood modelling software. And for those that are new to our webinars, please feel free to send message questions to us through the GoToWebinar pop-up box during the webinar, and we'll answer either throughout the session or after the session ends. To start with, I'll briefly set the scene, covering an update on the legislation and guidance available. This is going to be mainly UK based, but we have contacts globally. So if you're tuned in from overseas, then feel free to contact us and we'll help you with the local guidance. But I'll run through that before handing over to Ludmila, who will cover the theoretical and the practical aspects of flood modelling in more detail. At the end of last year, we sponsored and attended a SWMP conference on flood resilient communities. And during the course of the event, we had a lot of case studies, and this was based on the DEFRA Flood Resilience Community Pathfinder project scheme. The session was opened up by Rory Stewart MP. He's the Parliamentary Under Secretary of State at DEFRA, and he opened the conference with a keynote speech in which he confirmed that EA flood funding was protected for 6 years, covering both revenue as well as capital spending, and this was following the spending review. Now, apart from some very good case studies that I mentioned, here are some of the key points that really struck me during the course of the conference. First of all, the government acknowledges that we are experiencing the effects of climate change, and we have 300,000 properties predicted to be at high risk in the 2060s, beyond the year 2060. And this was based on the Committee on Climate Change report that came out in 2015. Now, everyone also needs to take responsibility, and this can be really difficult to obviously initially engage with communities that are at most risk. It's that early engagement and the initial engagement that's really difficult. And with regard to health, the emotional damage caused by the stress of just knowing that everything needs to be moved upstairs within a short time scale when heavy rain is forecast is indescribable by many people. There are also increasing numbers of community network groups, and these groups are helping to implement emergency plans, provide resilience measures, along with local knowledge and awareness of the flood infrastructure that's actually already in place. And many local authorities have helped to set up community groups with a range of toolkits and training to help improve communication and information at the local level. There are also emergency plans where flood guides have been often widely distributed and local flood wardens established in those areas at highest risk. And in those areas, there are warning signs, signage with grid references, telephone contact numbers on, for example, bridges that are at extreme risk have also been set up. And at the end of the day, a lot of the case studies did say that inspirational local people really help to drive local projects and local initiatives. So working together with these community champions really do help with the delivery of local schemes. Now, looking at the legislation, this cascades down from Europe, which is a very topical subject at the moment. The EU Floods Directive was first published in 2007, and this directive has then been implemented through local legislation, such as the Flood Risk Regulations, which came out in 2009, and the Flood and Water Management Act, which came out in the year 2010. Now, the Flood Risk Regulations accepted the EU Floods Directive targets, and those targets are shown here. There's a lot more in the regulations to this, but I'm just kind of concentrating on the relevant aspects in terms of the flood modelling side of things. You can see here that the flood risk management plans were submitted to Europe by the end of last year, 22nd of December actually, and that took place. But December 2015 is not the end of this process. In fact, it's really more of a new beginning. Because last Thursday, the Environment Agency published how organisations, stakeholders and communities will work together to manage flood risk over the coming 6 years, from now until 2021. And this is shown here. Going back 6 years, DEFRA published technical guidance on the production of surface water management plans, covering the preparation of the plan, running through risk assessments, optioneering, through to implementation and reviewing of the outcomes. As well as the surface water management plan type guidance, there's a range of guidance available. SWMP, through the Urban Drainage Group, which was formerly the WAPA Group, they provide guidance on modelling integrated urban drainage systems. So it really depends on what it is you're modelling as to which guidance we could sort of steer you in the direction of. Just looking at surface water flooding, just over 3 years ago, the Environment Agency published technical guidance on surface water flood mapping, and this was specifically generated to help the new lead local flood authorities that were designated in the Flood Regulations 2009, and their roles and responsibility spelt out in the Flood and Water Management Act of 2010. 6 months later, technical guidance on submitting locally produced information for the flood map for surface water was published. And again, this was to enable local updates to be incorporated into the Environment Agency's overall surface water flood map records. Prior to this technical guidance, DEFRA and the Environment Agency carried out a series of benchmarking of 2D hydraulic modelling packages. Now, this exercise was carried out, this particular publication came out in 2010, and the exercise was carried out thereafter. And XPSWMM and XPSTORM are the products that have passed this benchmarking test. And certain lead local flood authorities have a legal duty to prepare flood risk management plans. So this particular guidance came out on the 1st of May, and I've highlighted in red in the bottom right-hand corner of the screen here to show that by law, this guidance must be followed. So where we're at right now is that we have legislation in place, we have guidance in place, and the local communities rely mainly upon the local authorities, as well as the Environment Agency and their consultants, to make sense of some often very complex flooding situations. What we're doing today is helping you to understand how the technology can help to pull together such information from a variety of sources and to deliver a clearer picture of those existing risks, as well as providing a range of optional solutions to share those with the community to make really empowered decisions on moving forward together. So without further ado, I'll hand you over to my colleague Ludmilla, who will now go through the theory and the practical implementation of 2D flood modelling. Ludmilla.
Thank you, Peter. Good afternoon, everyone. I will start with a question: why flood modelling is required? First of all, flood modelling is required for flood forecasting, to identify level of inundation and related hazard to it. Zoning floodplain, to decide where is the best appropriate place for new development. It is used to define locations and levels of flood alleviation schemes. If you need to design a flood wall, how high the flood wall should be, at which location the flood wall should go to help alleviate the flooding. As well, it helps to build community awareness and convey communication to the public. Types of analysis available. Every day you hear a lot about 1D, 2D, 1D, 2D, 3D. So what it is? 1D is solution of the one-dimensional equation. 2D is the next step further up. It's a solution of the two-dimensional shallow water equations. 1D and 2D is the best of two worlds. So basically it combines 1D analysis with 2D analysis to give us more real-world picture. As well, there is something called 3D analysis, which is a CFD analysis, which we won't cover today. So what is 1D approach? One-dimensional equations are used to calculate single result for a cross-section. The cross-section can be an open channel, such as a river or a stream, or it can be a closed conduit, such as a drainage system. After performing one-dimensional calculations, we will get a single water level velocity of flow rate for the cross-section. Pros and cons of 1D modeling. 1D modeling is fast to solve. No matter what type of computer you have, you will be able to solve 1D model. it is great and good in point results. If you need to know your water level or velocity or flow rate at a certain point of your system, if it is a section of an open channel or if it is a pipe or a manhole, it will give you the result back. It is great for closed conduit hydraulics. What are the cons? No water or velocity distribution on floodplain. The flood modeling nowadays is a lot about floodplain and how the water spreads over ground. So with 1D approach, we won't have that. As well, it's a time-consuming model setup because you would need to define each and every single manhole and pipeline, as well every single section for your open channel to get the result. It is not good at presentation of complex overland flood routes. You can use 1D approach to represent some flood routes if you exactly know where the flooding will occur and which way it will go. But in real life situation, it's not like that. Typically, we don't know where the flooding will be and we don't know which path it will follow. What is 2D approach? 2D is two-dimensional equations which will calculate average results per grid cell. So average water level, average velocity, hazard rating, or flow direction. In the graph here, we can see that there is a bridge from a dam and the water flows down and it floods the floodplain, and with 2D approach, we can see what effect it will have on buildings and people lives who will be affected by this bridge. 2D modeling is easy to build. It takes into account overland flood routes and structures are considered. Such structures as buildings, dams, flood walls, different defenses, substations, or any other items which are located within floodplain can be considered. What are the disadvantages? It could be slow. If you will have a quite big model with a very high precision, it will be slow. It needs a good DTM. Without a good DTM, the 2D approach has no life and it cannot survive, because unless you have a good digital terrain model, you cannot predict good levels and good values out of it. As well, it's unable to represent small features. So if you have a little house, which is maybe 5 meters by 5 meters, it can be a shed with tools or a garage. And if your cell you're modeling with is quite big, let's say it's 10 by 10 meters, this little structure will be completely ignored. So 2D has its pros and cons. What is 1D 2D approach? Basically, 1D 2D approach is a combination of best of two worlds. You still can have as a representation of your drainage systems, all the elements like manholes, and you can have representations of 1D natural channels, plus two-dimensional approach for floodplains. So you will get two sets of results. The average results per grid cell, like water level, velocity. As well, you will benefit hazard maps and other type of results you can generate out of 2D approach, but same time you still will be able to go back and check your 1D levels, 1D velocities, 1D flow rates. Picture in here, which I choose to put in, is a great example of 1D 2D approach in real life. We have a gully which floods out to the surface. So there is a drainage system underneath the surface. The gully is connected to a drainage system. A drainage system meets its capacity. It starts to exceed the flows on the surface, and we can map these flows, where they will go, what will happen. But at the same time, we can still monitor what happens inside the underground system. So typical 1D, 2D linkages. You can have a 1D network, then a surface, and another 1D network. So basically, you can have a drainage system which will flood into a surface, and then it will flood back into drainage system. You can have a drainage system which is embedded within the surface, like in a graph here, where the flow will go through pipes If the pipes exceed its capacity, it will go out on the surface and it will find somewhere a location where there is still capacity to go back into the system. It will go back into the system. As well, if we are talking about open channels, the open channel can cross the 2D domain and be considered as 1D open channel, and everything around as 2D. Same time, we can connect a drainage system to our river channel and have a complete combined model of 1D, 2D, including open sections and closed conduits. So which one to choose? 1D is good for drainage system sizing. If you need to understand what size of a drain you require to drain a certain catchment, it's good to do that. If you have a water course which you know has no flooding historically, but you need to prove to a approving authority that there is no flooding, you can just create a simple 1D water course model to show that, okay, even in a big rainfall event or a big storm event, the water level doesn't go much up and the capacity isn't exceeded. It's perfect for detailed design and related analysis. The pure 2D approach is very good for preliminary flood risk assessments, breach analysis, and quick inundation calculations. If you have a piece of land and you need to understand what would be the maximum water depth if a 100-year rainfall event comes, just to have a quick idea what will happen on the surface, pure 2D is a great approach. It's very quick to build, it gives you the results straight away, and you can make the decisions about your new development, planning, or anything else, or maybe some decisions about flood alleviation. Very high level. 1D, 2D is great for detailed flood modeling, accidents, blockage, and it's ideal for urban areas. The places we live in are villages and towns and cities, and they all have drains inside them. They have pipes, manholes, drain infrastructure, but as well there is a lot of adjacent land to it where we walk, where we live. And what happens when the drainage system exceeds? The picture down here shows like a nice fountain out of a drainage system. Basically what happened, the drainage system got full and the water started to flood out at a low location, and the pressure was so high inside the system that it basically lifted the lid and just started to escape. And with 1D, 2D approach, we can map and manage and enter all these details inside the model to get the most realistic results. When it will happen, how it will happen, and what the impact of this event would be. As well, if you have a system and you would like to do some blockage analysis, the system is there and it will still take some water, but a certain amount of water won't get in because the drain is blocked. So what will happen to this water? Where will it go? Where will it pond? Will it affect any of the houses around? Where there will be any significant flooding implications? Unless you have a 1D, 2D approach, you are unable to take into account both drainage system and overland flood routes. In 2D calculations, there is a lot happening in the background. That's for why it's slower than 1D calculations. So this is just a formula which is used for a 2D equation solver. It uses this formula to calculate for each and every time step, for each and every grid cell, to give you the result. One of the differences in between 1D and 2D analysis is how the energy losses are handled. When water changes speed and direction, it loses energy. This is an additional loss that occurs besides the bed roughness. Open channel bands is one of the examples where water is forced to contract and then expand. The energy loss is very dependent on the velocity of the water. So if the velocity is, say, 1 meter per second, dynamic head would be only around 5 centimeters. But if the velocity will be much higher, let's say 4 meters per second, the dynamic head will be in a range of 80 centimeters. I will show you one example right now. On the left, I have a 1D model with 90-degree bend. and a band is located at location A. So the 1D model does not know there is a band unless we specifically specify it as a loss. Unless we go inside 1D model and at this location we will say, okay, there is a band which is associated with an energy loss. So if we don't do that, the 1D model will never know if it bends right or if it bends left or if it goes straight. If we create a little 2D model and generate flow patterns, as you can see on the right, the flow deviates from being a normal flow to being a more complex flow. At location A, you can see there is mounting of water. The reason is the water is slowing down and kinetic energy is converted into potential energy and the water level rises. So here you can see how the water level rises before the bend and how it then drops down after the bend. Importantly, the upstream water level is higher. This has a fundamental differences in between 1D and 2D equations. With full 2D equations, water will lose energy where it's forced to turn or change speed. And this is not only applicable for, let's say, river analysis or any type of man-made or naturally made channels. It is as well applicable for narrow streets in the towns. If you have houses and if you have curbs and your water is forced to change direction, if it's forced to meet an obstacle, the 2D analysis will give you the super elevation, which you can see in here, where on the outside side of the bend, the water level is much higher than on the inside side of the bend. And if it's quite wide and the velocity is high, there is a lot of volume of water, this difference may be tenths of centimeters. So for bigger rivers, it could be even a meter difference when the river bends. For streets, it can be few millimeters or centimeters, but it all depends how much water you're having there. The other thing 2D brings to your analysis is improved results. With 2D approach, we can choose how good the results we want to see, how precise we would like to see our results to be. In here, there are just 3 examples of a same analysis. There is a bridge, and we modeled it with 20-meter cell, 10-meter cell, and 5-meter cell. So you can see the difference. In 5-meter cell, you can see how the water goes in between the structures or buildings. In 20-meter cell, we just have, let's say, an indication of where the water will go. Same if we would switch on the water depth map. In 20-meter cell, we will have one water depth for 20 meter. In 5, we will have a water depth for each 5 meter square. Another item 2D modeling brings is ability to define buildings and different structures in 2D. There are different approaches how to define buildings in 2D, and I will go through some of them today. One is completely block 2D cells out where the buildings are. So we will have no water going through the building, we'll have no storage within the building, and 100% of flow will go around the building. It is a quite good approach when we need to do some high-level analysis and we have a bunch of buildings and we just need to identify what is the highest possible level occurring. But it's not always very accurate if you would like to model real-life scenario. In here, this is just an example of buildings as inactive cell with 2 different resolutions. There will be few examples with different resolutions, so this is one of them. And you can see how decreasing the cell size improves your results. So in here, we don't see any flow going in between these buildings and very little in between here. So if we go to 2-meter cell, we can see a much better representation of what happens on the surface. The next approach would be model buildings with 3 side walls. It will allow us to have some storage represented. So basically, yes, we can have some storage. The water won't go exactly through the building as it may be in real life, but the storage will be there. So when we use this approach, it's quite important to remember that there should be a threshold level for the structure itself, because we still need to represent the energy loss when the water hits the building wall. And this is just a map showing the building with 3 sides, we can see that there is some water inside the buildings, and this is 2 by 2 meter, so just a better resolution of the analysis. As well, there is a high roughness approach. Typically, it's used for very big grids. When you have a big area and a lot of buildings, say a city center, and you would like to see what would be the effect of it, what it will do, it will slow down the water through the structure. But typically, the high roughness, we would recommend it to use with some threshold level or 3 sides as well. Just consider the storage as well. So in here we can see the high roughness example and the more dense high roughness example. Basically, you can see that the effect of water hitting the building wall is not exactly represented when you just use high roughness approach. 2D allows us to model such items as fences as well. In detailed modeling, when you look at a very small area, a fence can be very important because it may slow down the flow, it may change the flow direction, and it should be considered. And a lot of us sometimes simplify things and we don't consider such items, but it can be crucial. It can change the whole map and how it ends up to be if we ignore the fence. Blockages. Obviously, I did show an example of how the drain can be blocked, but as well there are different types of blockages, like blockages on rivers and open channels. So this type of handrail, this is recommended as it does not collect debris, but you can clearly see there are trees growing there. So some agencies require that all rails are blocked. There are different approaches how you can represent blocked rails in 2D. So if you have some rails, it doesn't need to be a rail above the river. It can be any different type of rail which may be exposed to blockage. And there are ways how you can represent blockages in 2D. And sometimes we can even have a blockage like that. It's not very common, but it happens. Now I'm going to show you a very small model, but very good model anyway. So this is a very artificial model made specially for this webinar to show you the benefits of what you can do better when you go with 1D to D approach. This is a small DTM which goes from 2 meters down to 90 centimeters. It has 2 1D items in that, 2 systems. Each system consists of 2 manholes and 1 pipe. So system number 1 is manhole 1, manhole 2, and pipe 1, and system number 2 is manhole 3, manhole 4, and pipe 2. In manhole number 1, we have a user inflow hydrograph, which contributes some water. And this water will go through pipe number 1, and then it will flood out of manhole number 2, which is linked to 2D. So manhole number 2 will contribute all the flooded flows to 2D, and then this water will go through to the surface, and it will enter manhole number 3. So if we go down here, and if we open manhole number 3, we can see that manhole number 3 is set up to capture to the inflow. So what will happen? All the water will come down towards manhole 3, will be captured by this manhole. And then it will go through pipe number 2 and exit through free outfall at manhole number 4. So obviously the outfall condition can be changed, but for sake of example, it's a free outfall, not to confuse the results. So I will take a water depth map and velocity map, and I will click play to see what happens. Our hydrograph runs for 4 hours. So let's see. The step I'm presenting it is 10 minutes. So every 10 minutes we see a different picture. We can slow it down to show it every minute or fasten it up to show it maybe every 20 minutes. But what we can see is that basically node number 1, which is manhole number 1, received water, conveyed it through pipe number 1, and then it started to flood out of manhole number 2. And as the hydrograph was going, the water was flooding, then the hydrograph stopped, and then the water started to flow down naturally using the grade of the DTM towards the bottom side of the DTM and contributing towards manhole number 3. So when we end the simulation, at the end of simulation, we will have a little ponding down here, and this ponding would be due to very shallow water levels. So in here we see water depth, and you can see it's 1 centimeter. So basically 1 centimeter is not enough head of a standing water to drive it somewhere. So it will be just like a little puddle of 1 centimeter, which will eventually evaporate. But the interesting part of this model, it's not only see graphically how the water moves, but as well, if we go inside 1D part of the pipes, if I select both pipes and go to the graphs, okay, I'm sorry, not this one. If I go to the graphs, I can see the pipe 1 flow against time graph and pipe 2 flow against time graph. So pipe 1 is mainly repeating the hydrograph. So it starts at time 0, goes to the peak, and goes back at 4 hours to 0. Nothing else happens in there. But if we look at pipe number 2, the receiving pipe, we can see that there is a delay of around 45 minutes from the beginning of the simulation till the point when this manhole starts to receive water. And then this water is received over time, and it ends around 5 hours. So remember, our hydrograph was 4 hours. So, and pipe number 2 starting to receive flow in around 45 minutes, and it ends in around 4 hours, 50 minutes. So basically, it's shifted. There was a delay from when this second system started to receive water and when this second system stops to receive water because of the time the water needed to travel overland to reach manhole number 3, where it will be collected for further conveyance. This type of model obviously is very simplified, but if you have multiple drainage systems and you have some flooding, and you don't know sometimes what if it floods out of one system and enters another system, or maybe it floods out at an upstream end and then it will rejoin the system at the downstream end. You can't do all this type of analysis using just 1D approach. You need a 1D, 2D model being set up to basically model the real life scenario. And that's it from me for today. I hand you back over to Peter.
Great. Thank you, Ludmila. I hope you enjoyed that as much as I did, folks. It was really interesting. So just to draw some conclusions from that, the 1D is used for those closed systems, typically those pipe networks under the ground. It may be a surface water conveyance system. It could be a water course, a river, a ditch, or whatever. But that's the most accurate way of representing the flow within the 1D. But what happens when that water comes out of the channels or out of the manholes? Where does it go? This is where 2D analysis for the overland flood routing comes into play. So ideally, it depends on the situation and the kind of work that you have. So you could use 1D, you could use 2D, but typically we're combining both to get the best of the both worlds. So combining 1D and 2D, you get the benefits of both in the one model. Looking ahead to the next month, in fact, looking ahead to tomorrow, just before I mention our sessions coming up in April, tomorrow, if you haven't already registered or attended, I'd recommend that you log on through Engineering Nature's Way. There's a really good series of presentations run by Mark Goodyear at Hydro International, and there's a go-to webinar tomorrow lunchtime, which is on water quality design in accordance with the new SEDS manual C753. So if you haven't already booked, then go to Engineering Nature's Way and you'll be able to register for a free webinar on Series C753 with respect to water quality. So looking ahead to what we're doing over the next month ourselves, 11th to the 14th of April, there is training here in the Newbury Training Centre, microdrainage training. On the 19th of April, I'll be running a micro-drainage webinar. The last one before I went away on holiday, you may remember, was on designing of a storage structure. And what I'll do is I'll take that forward a step, and we can maybe look at the water quality issues that Mark will cover during his presentation on the SUDS manual tomorrow. So we can incorporate not just water quantity, but water quality. We could start to look at the flow of the water through a structure. So Ludmila's been running through the modeling of systems and catchments, either large scale or small scale catchments. We could start to look at modeling the flow of water through a structure itself. So that's the kind of content that I'm planning to put into the 19th of April webinar. We'll send out registration details and a separate cover following this particular one as well. And on the 20th to the 21st of April, 2 days, there's an annual SWMP conference being held in London. Ludmila will definitely be there, so feel free to come along and meet the team. Ludmila and my colleagues will be there for 2 days on the 20th and 21st of April. Again, go to the SWMP website to register for that particular conference. And then we'll have training here at the end of the month, 26th to the 28th, 3 days of XPSWMM training being held here at the Newbury Training Centre. So I really appreciate your participation. Thank you very much for an interesting and informative presentation there, Ludmila. I hope you all enjoyed that as much as myself, and hope you're all enjoying Easter as much as Ludmila and I. So
thank you, Peter. Happy Easter to everyone.
Happy Easter, folks, and see you again on the 19th of April. Take care.
Bye.